Yes, first of all, of course, thank you to the organizers, Christina, Christos, Marcus. This is a wonderful venue. I have to say it's really great to be here and have the opportunity to talk a little bit about where I see some future directions when we now go into quantum, which I think is the title of this workshop here, Quantum Functionalities of Nanomagnets. So what I'm going to share with you is a little bit my vision, my perspective of the future. It's green. Yes, it's green. So can anybody hear me? Okay, it's better now? Okay, anyway, so it will be a little bit looking forward, and I hope I can trigger some discussions among particular the more junior colleagues here, what they might be doing in 10, 15 years down the road. Maybe it doesn't take that long. It's particularly going where we are today and moving to the future. If you ask about this background image, have I ever published this? No. Will I ever publish this? No. All I want to have is a nice background image that captures a little bit the title, and I just used AI and said, tell me what do you think would a picture look like? And this is what it came up with. So you make your own kind of conclusion what this is looking like. Anyway, I also want to acknowledge here the funding by the Department of Energy. So this is a brief outline what I'm going to talk about in the next 20 minutes or so. First, I want to give you my little kind of brainstorming. What does it really mean, nanomagnetism, when we go from classical to quantum? And we've heard this morning from Marcus already a lot of topics. I'll just throw them out, and you pick whatever you want as a topic that we want to do. And I'll share with you a couple of topological spin textures. And I put the quantum in parentheses because we're not yet there, particularly when we go into X-ray microspectroscopy with this. But it's clear, obvious what we want to do in the future. And then the last topic, I want to share with you some very exciting stuff, which I believe might have some implication to this topic, which is X-ray vortex beams. And for those of you who have been here, this place last week, probably none of you, there was a SPICE workshop just talking about OAM beams, optics, electrons, and X-rays as well. So just a coincidence. I don't know whether I did it on purpose, but it's just wonderful. Okay, so here we go. Just a couple of terms that, again, you can pick when you think about quantum. I think you should talk about those kind of themes here. And I will not talk about any of those right now. But if you think about what is the future when we go with skyrmions into the quantum regimes, I mean, we can think about, can we do some entanglement of skyrmions? I don't know. I mean, just bring it as an appetite for you. And you go all through this quantum coherence, tunneling, quantum phases. The last one here is probably the most relevant here. Can it be at all applied to quantum computing? And if you ask me right now, where there's, of course, funding available, at least in the US, it's about quantum computing. So let's think about, can the science that we're doing right now being applied to quantum computing in skyrmions? Now, where do I feel is our mission, particularly where we have to go coming from material sciences at Berkeley Lab? How do we bring actually basic material sciences into the quantum computing? This is, I think, where I see our mission. We need to understand fundamental material science. We need to develop new materials. We need to discover new materials. Characterize them. And when you think about materials, what comes to your mind? In the end, materials are made up from electrons, and electrons have a charge and a spin. So in the end, what you need to do is somehow play with those little Lego blocks here. And of course, we all know charge that has led to electronics. I mean, that's not what I'm particularly interested in. Basically, they run charge currents around, and you build the electronic CMOS technology and things like this. And on the other side, when you think now about the spin, and now we come down to the grand challenge about beyond Moore's law, how do we actually decrease the power, low power electronics and things like this? Maybe the spin is really the future. And I mean, if you ask me, yes, I'm biased. I think spintronics is the way to go. Think about how we can manipulate the spins, how we can build spin systems and play with this. And we'll hear throughout this entire workshop here quite a bit of this, whether it's even magnonics as one way of manipulating the spins. Anyway, now we talk about quantum information. And I'm not quite sure this is a real straightforward arrow there, but I just want to mention, a lot of people think about superconducting qubits, which is, of course, companies even involved trying to build these superconducting computers. Open box here, just leave it open, because I will not answer this question here. Can the skyrmions that we mostly talk about here be then built as qubit systems in the future? Is this, again, far looking in the future? You need to probably think about these quantum properties as well of this. And maybe this is what we want to discuss here exactly at this workshop here, a little bit this kind of future vision on all of this. So now, this is, and again, Marcus also started his talk with this very nice review article, and maybe Alex will also show a little bit about this. this was then when we put this together, and I thought how we actually exemplify experimental challenges when we talk about bringing now skyrmions to the quantum regime. And this is just a cartoon, what I believe the axis that you have to actually address from an experimental point of view. I mean, quite obvious, you need to come down small, you need to go on the length scale. I mean, all the way down to, let's say, the angstrom regime. Spatial resolution is important to do. Multidimensionality is, of course, another one. Energy-wise, of course, we'll probably talk about tiniest or smallest, energy levels that we need to deal with. Timescales, we already talked here about what is it that we can do. It needs to be fast, so bring it down to very fast timescales. And also temperature, we probably need to go. I think Marcus and others mentioned about this, systems at a very low temperature regime. So in the end, bring it all together in experimental techniques. Think about what could the experimental techniques be here. I just put up a few of them, and we'll probably hear more of those even throughout this entire workshop. I will just briefly catch up or mention a few of those that are related to what I feel are X-ray based science. So X-ray means you go to a synchrotron, you go to an X-ray free electron laser. This is where right now you can do this kind of experiments. You can even think about some tabletop high harmonic generation X-ray sources. X-rays as the probe to study those topological spin textures ultimately in the quantum regime. I will talk about a little bit about some ultra-fast nanoscale spin fluctuation experiments that we've been doing at SLAC a while ago. And since Marcus even mentioned fluctuation to be one of the keywords for quantum systems, I will share with you how we can do this with using so-called XPCS at free electron lasers and really understand nanoscale spin fluctuations. I will not talk about this beautiful work at Argonne, where they basically combine in the end an STM and put it into a synchrotron. And now they have all the capabilities from the X-ray source, elemental specificity of this, and combine it with STM capabilities. I really enjoy this work, and I think this is one of these kind of new directions that you might be considering become part of this as well. And on the other side, on the left side, definitely have something like nano-ARPIS. I mean, we haven't talked about ARPIS at all, but I would assume any 2D materials, nano-ARPIS is kind of a standard techniques that you still want to go for. Mapping the band structure with a nanoscale resolution as one example, and momentum microscopy is slightly related to this. So, brief overview where I see historically, legacy-wise, how we got into this business of topological spin textures. Down there's a timeline, and you can look back probably around the mid-90s or so. Experiments, again, started trying to do some imaging of vortex structures, permaloid vortices. Who didn't look at permaloid vortices back then? People were just excited about this, which is not really, at that time, was considered to be a topological spin texture, but I think now, looking backwards, where we should have started talking about this. Then, of course, it got really excited when we started looking into the so-called classical skyrmions. We heard about this morning, the introduction. This is characterized by the skyrmion winding number. Hopfions. A few people ask questions about hopfions. I feel this is also a very exciting new topic to go for. Basically, you go from this classical skyrmion picture, which, as you can see here, is basically, in the cartoon, always meant to be a two-dimensional structure. Now you put this in a realistic material that has some certain thickness, and you ask a simple question, wait a bit, is the spin texture throughout the entire stack the same? When you take a slice, can you imagine that this is always the same? The answer is simple. It can be, but it's boring. If it's not, it gets interesting, and then we have the skyrmion tubes. We talked about skyrmion tubes already. Start twisting them, build a torus. I mean, simply speaking, you end up with something like a hopfion, where now you have isolines of magnetization that just wrap around such a torus. And when you unfold them, basically you have something like linking. And now you have a new topological number, the so-called linking number, which can only exist in 3 dimensions, right? There's no way that you do the same in 2 dimensions. Again, this means we also need to go with our topological kind of experiments into the 3rd dimension and really try to analyze in 3D all the spin textures. And I will share with you in one of my next slides a couple of those recent examples. And of course, the last thing is now we'll be in topological, in quantum skyrmions, and maybe I should put here 25 and a little bit to the right, because I don't think we're yet there, particularly not with X-rays, to do experiments on quantum skyrmions, but we will get there, I'm very optimistic, anytime soon. And of course, we heard about this, not only this groundbreaking paper, Lohani and others, but also then again, if you're interested, what I think we put together a nice overview in this RMP article here. And of course, it's now, the difference is, you'll have no longer skyrmion, the magnetization to be a classical kind of vector, but it's now the expectation value of the local spin vector operator, and Marcus gave a beautiful introduction in this entire topic here. So that's, I would say, kind of on a timeline. So if you think about how I plan my professional career in the future, I want to do this, keep that in mind, and just imagine where you want to jump in and finally do it. Okay, a couple of experimental validations now. Now let's come back to the experiments, particularly looking into X-ray-based techniques, and I'm not sure we probably will hear more about X-ray scattering techniques as well, of what I call unconventional topological spin textures here. And I'm just really highlighting here 2 examples. There's lots of them in the literature right now because people get excited about this and use the X-rays to image those. Particularly, I just want to highlight here this work by Burge et al. In 2020, where they looked into so-called skyrmion tubes, and they had a lamella of an iron germanium. Iron germanium is one of those prototypical materials that people are very excited about when they look into the topological spin textures here, and they combined X-ray diffraction with holography, and very interestingly, they found probably by analyzing data some block points at the very bottom of this skyrmion tubes. Yes, again, block points are fascinating objects to look into, and we have now the capabilities to even image those and then try to analyze them. And this work here on the right was an experimental verification that our group did together, in collaboration with people in Berkeley as well as in Spain. And we designed on purpose a multilayer where we had the PMA varying across the depths of the multilayer. In the end, by doing so, this was driven also by some theoretical predictions, we basically forced the spins to form these hopfions within a kind of confined structure. The big question is still with hopfions, and this is what I'm very interested in right now personally. Can we even make a material that has a hopfion lattice? How do we design, and what would be the parameter to play with to build actually hopfion lattices? We know how to do this with skyrmions right now, whether it's the carboxyl selenide or whatever. I mean, the recipes are out there. Just let somebody make the sample, and you will see the skyrmion lattices easily, gadolinium iron and multilayers, all of this. Hopfions, I think the race is out there. Who will be the first to finally have this material ready to do this? And then, of course, in this topological spin textures, and I want to go back again what we just heard from MFM, I mean, cocoons, Albert Fair's group looked into these cocoons. Again, designing a very interesting multi-layer structure. So you basically design the material in a special way, and then you build these topological spin textures. And on the hopfion side, again, very recently, some beautiful work using now electron holography and Lorentz TM in an iron germanium crystal. This was the Jülich group, and they were able to design and stabilize a hopfion structure that's kind of surrounding skyrmion strings. Beautiful work. Again, this is where we are right now from an experimental point of view. So, and now I want to feature with you an interesting recent study that we've been doing, which I think points a little bit to what X-rays are capable of doing. And this, in the end, led to a full 3-dimensional reconstruction of the spin texture in a single skyrmion. As I just said, I mean, skyrmions, you always listen to the talks, and everybody shows kind of this 2-dimensional cartoon. But again, as I said, when you put it in a realistic material like a multi-layer system, you have a thickness, and it's not obvious, and it's not natural, and not given that the spin textures look exactly the same, the way how the winding happens throughout a slices of layers. We built, again, and this was work in combination between the Nanoscience Center at Berkeley Lab, Molecular Foundry, where we kind of had e-beam lithography. Western Digital helped us to make a perfect interface-wise multi-layer system. Just to give you a couple of numbers here, 800 nanometers across and about 95 nanometers high, and each layer was about a couple of nanometers of cobalt and platinum. Again, very, I mean, tiny, and I would say almost getting really relevant to some applications there. MFM, just use them as a pre-characterization tool. We saw target skyrmions, and then actually took it to the Swiss light source, and this was really beautiful work. I think it was the last experiment before they shut down for the downtime. Last experiment, the Pollux beamline. Together with Simone Finizio. And in the end, we did some laminography, and were able to get a full 3-dimensional reconstruction of the entire skyrmion. And this is now the rendering here in the center of this single element here. And now once you have the data in the computer, voxel cells of about 20, 30 nanometers, now you can start playing with the numbers, and you really cut slices in the computer, and you start analyzing and quantitatively characterizing the spin textures at every voxel, at every slice across, and do this. Not only you can easily come up now with the MX, MY, and MZ component, because you have the data. I mean, basically, how does the limonoscopy work? I mean, you rotate the sample around, and you take projection images, and then reconstruct them in the computer. That's the tomography system. But you can also now take slices, right? And blue and red means actually this is now an experimental verification of the winding number. You just see how they rotate from red was probably down, and blue was up. See exactly how it rotates. And then when you start analyzing throughout the entire stack, from 80 nanometer was on the top, 60 nanometer, 40 nanometer, 20 nanometer, and then you start plotting actually the winding number as a function of depth resolution, or as a function of the depth. And what you see in these graphs here, it's not the same. It matters whether you are on the top, how it's winding, or whether one layer down, or 20 nanometer spatial resolution wise down, and do the same thing. This means that the local energetic landscape in your three-dimensional system determines how fast or how slow the winding number changes from up to down, or from down to up, which means there's a depth-dependent radially profile. It's a little bit similar like what people knew many, many years ago from vortex cores in a permaloid disk. This is also not just a straight line. This is kind of a barrel-like. But anyway, we were able for the first time to quantify this by doing real experimental data. And X-ray, this tomography variation, I think, was the key here. My student also then started analyzing actually the character of the domain walls within when you are going from this, let's say, from the red through the white was the domain wall to a blue area. And he basically just plotted some numbers, an N and an M and the beta version, and then plotted as a histogram, and to see what's the character here, the domain wall angle, just a histogram. And he found, for instance, there's a primarily positive nail rotation of the domain wall. Again, in 3D, and you go through all the stacks, right, from 80 to 20, all the way down. So in 3D, you see a lot of variations that you would not naturally assume in the first place. Now, in the reverse, you can say, well, that was just an imperfect sample. Now, you can also say, maybe I can design now a sample that does exactly what I want them to do. So it's, again, this going back and forth between the prediction and then the properties. And if you wanted to do that kind of rotation of the spins, well, you just design the material in a special way. So this was really very interesting. And we went even one step further, which was then quantifying fundamental magnetic parameters in 3D. Because XMCD, the magnetic contrast that we're using, the dichroism, has some relationship, of course, to the magnetization and to the PMA and Heisenberg and so on and so forth. And I mean, I'm not saying that we were able to determine now fundamental materials parameters. We assumed they are the same because we knew exactly what materials we had. But we were able to plot some profiles of, let's say, the PMA energy density or the Heisenberg energy density or the Chalchinski-Maria energy density. And it shows some variations, again, across the various thicknesses. So again, take-home message here is, if you go into 3D and characterize in 3D, you will see non-trivial variations of the material, and you get a representation of each individual voxel cells, volume cells inside your element. And I think this is relevant, scientifically interesting, but also technologically absolutely relevant. Any materials that you will sell on the market will in the end be a three-dimensional system, and therefore you need to understand it. Okay, let me switch quickly to the ultra-fast fluctuation experiments that we've been doing a while ago. We used the technique, a relatively new technique at the linear coherent light source in Stanford. And of course, we used the high coherent flux there. It was basically X-ray photocorrelation spectroscopy. So we used, we put actually a double pulse of an X-ray FAL, very short pulses, and we're shining through the material and then capture these kind of intertwined kind of data in the detector. The student, Matt Seberg, I think probably spent months in analyzing this data. A lot of autocorrelation techniques were involved. I don't want to go too much into detail, just saying that we are able to study fluctuations down to about 350 picoseconds, so very short time scales. What was really interesting, this is just what I want you to take home here, is we looked into an iron, gadolinium iron multilayer system, standard, a fruit fly that we did a lot. And we knew from previous experiments that we can tune this material, the spin texture, from a line pattern into hexagonal skyrmion lattice pattern by just slightly going at room temperature from, I don't know, 210 to 210 millitesla applied magnetic field. By just doing this phase transition, you force the spins to go from a line arrangement, regular, a stripe line domain pattern, into a hexagonal one that is visible, for instance, here in the diffraction pattern. And now what's interesting is these data showed that a characteristic timescale of the nanoscale fluctuations depends whether the system is in the line phase, in the stripe phase, or in the hexagonal lattice phase, which you might say, that's surprising. Why would all of a sudden these fluctuations, feel whether they are arranged in a stripe pattern or in a hexagonal lattice pattern? And I don't think we have yet an answer to that question. I think we probably need a lot of theorists to help us with this, but it's obvious from the data. You just see that kind of this thick line here, the orange one, and the blue line in the same time scale down here. This is way slower, and this is way faster. So the fluctuations somehow die faster if they are in the stripe phase than in the skyrmion lattice phase. And if you have an answer, please talk to me. I would be still very interested to study this. Anyway, these are kind of experiments. What I want to say here is we can use now X-ray free electron laser, highly coherent sources, highly intense sources, high brightness sources, to really study ultra-fast nanoscale fluctuations in topological magnetic systems. And I think this is one of the characteristic probably directions when we go into quantum topological phases of the future. So this is clearly a tool that I think we should explore more and more in the future. Okay, now let me briefly touch for the last couple of minutes, about what I really see to be a new frontier in X-ray science. And I just want to exemplify this here with the ELS. ELS right now, Advanced Light Source in Berkeley, so our synchrotron, is undergoing right now an upgrade to what's called diffraction limited storage rings. And in the end, the goal is to produce highly fully coherent X-rays. It's really making these synchrotron sources, like the free electron laser sources, fully coherent X-ray sources. This is exciting. And I think this is now what we're seeing in the community, what the optics community has seen when the laser was invented. Before that, you had incoherent light sources, a light bulb, all of a sudden you had a laser. And there were experiments possible that were impossible before. Imagine this will happen now in the X-ray world. What is the difference? Very simply speaking, optics is about a micrometer length, wavelengths. Now we talk about nanometers, sub-angstroms, or angstroms, coherent probes. And this by itself should just trigger your imagination what you can do with these new capabilities there. So ELS really wants to be the world's highest coherent flux synchrotron light source. In the end, what we'll do is we'll squeeze the electron bunch which generates the X-rays to a diffraction limited spot. That's all what needs to be done, very simply. It's very complicated. With so-called multiband acromate lattice, you just put my magnets in the beam and then, or in the storage ring, and then you basically shape the electron beam, and then you get from this coherent light coming out. This is a cartoon. I'm not sure it's the latest, but anyway, shows how this is across the world from all the different synchrotrons with light source, for instance, here, and I think they just came back into operation. They've done this, APS, ALS, NSLS. So all of these sources want to go at some point to this kind of coherent sources. Max 4 is one of them. Sirius, it's Brazil. So wherever you're coming from, I think there's a place in the near-term future where you can just take advantage of these kind of coherent fluxes. This will allow us to really resolve nanometer scale features and also real-time observation of chemical processes. Just keep that in mind. Will be realized more or less around the world in the next few years. Talk about 10 years or so. But anyway, planning your career in the future, if you're interested in this, I would say please join the team, join the party, and be ready for this. So now what coherence really enables, and this is now a little bit my take-home message again here, we will enabling so-called orbital angular momentum X-ray beams. And what I mean by that is this will, and actually this was the workshop last week here, has been realized in electron microscopy. So if you're working in electron microscopy, one of the, I would say, quite exciting recent developments was to basically put a grating in the electron beam, and you basically make the electron beam in the microscope with a helical wavefront. Basically start bringing orbital angular momentum into the electron beam. Ben McMorran from Oregon, this science paper, I think he probably showed up to about 100 H-bar in the electron beam, which is a huge number, right? How can this be used? Remains to be seen. Now, this is nothing too new. The optics community has looked into this already years ago, many years ago. Topics about this is, for instance, twisting light, optical tweezers. for sensors being used. I mean, this is a lot that people are looking into right now. But again, I think the weakness is optics. You have this micrometer wavelengths. X-rays and electrons, you can really bring this down to a relevant atomic scale kind of length scale. And this probably makes it even more interesting. Now, generating the so-called X-ray vortices, which is another term for this, has been also demonstrated. I mean, this is one paper from ALS, Sujay Roy actually, and James Lee looked into this. They were able to build these so-called phase-structured beams. So that means across one wavelength, you have more than one rotation of the phase. This, in the end, is what you generate. You need a coherence for this. This will allow us to do completely new spectroscopy, scattering, and hopefully also in the future imaging modalities. The spectroscopy and scattering is probably the most straightforward experiments that people will do very soon. The imaging remains to be seen because the beam itself has a so-called waist, and it's a little bigger than just this few nanometers. But anyway, it's exciting. We might have to play with some of these fancy optics here, and I'm not sure you've seen Fresnel zone plate optics typically don't look like a spiral, but you can build them in a spiral. And if you put those into the beam, then you do some wavefront shaping with this, and there's, of course, a lot that you can do with this. So again, big question, I would say, that we hopefully might be able to answer with these kind of new beams here. Can we somehow distinguish quantum behavior from classical effects in complex materials with using those kind of beams? Right? All of a sudden, you have a new probe that you use here. I don't know about entanglement mapping. I mean, haven't thought too much about this. But it's pretty obvious that it will be relevant, I would say, to regular spectroscopy, scattering, and somehow also to the, I would say, latest advances in X-ray imaging, which is coherent imaging, holography, tachography, laminography. These are all the tools of the future that are being developed as we speak. Relies a lot, of course, on data science, data management. The amount of data that you get out here just to get one single image is quite big. But there's now algorithms being developed. So as a user, if you come and say, I don't want to deal with all this big data, I would say you just go there, bring your sample, and let, in the background, somebody else basically help you with analyzing the data. And it should be as straightforward to take an image out of this as you're used when you have your, I don't know, iPhone and to take a picture. That's, of course, the vision of the future. So don't be afraid to enter this field and say, I don't even know what I'm doing. I just see some diffraction images. Don't be afraid. Now, let me just explain a little bit what I think could be interesting for these orbital angular momentum beams when you just look into simple absorption spectroscopy. And this is an X-ray absorption spectroscopy. So in the end, what happens is an X-ray comes in. And as we all, or as you probably might know, this is determined by the so-called Fermi's golden rule. If the energy of the incoming photon matches the binding energy, let's say, of a 2p3f electron, you are at the so-called L3 absorption edge. This is known from textbook. What happens is then finally an electron is actually transferred from the initial state here, which is very well defined. That's the beauty of having X-ray inner core, the spectroscopy, into a D-band at the Fermi level, right? What's happening here, right? At the D-band here. So that means you have a P to D transition. Why do you have a P to D transition? Well, your photon has one h bar, angular momentum conservation, photon is being absorbed, P to D. There's also P to S. It's not that big. So in this simple process, which is well known for decades, energy is, of course, conserved, as I just said, linear momentum is conserved, and the orbital momentum is conserved. Now imagine, and of course, then magnetic means you also take into account the spin angular momentum of the photon beam, which is the circular dichroism, left and right circular polarized light. You have then spin polarized electrons within the solid. But now, what if you have now one photon that has more than one h bar? Right? And this is exactly what I think is the new thing to do. All of a sudden, I think it's not just the P to D transition that you're probing. You can probably go from a P to F in one step. And that, I think, opens up opportunity for completely new spectroscopy. You are able to see now new states that you could not go in the single step so far, but you should be able to do this. And this opens up, I would say, new opportunities to characterize materials and see something absolutely new. And of course, we might then also come back to this dichroism effects. And this is just hypothetical here, not yet proven. So far, XMCD, probing magnetism with X-rays, is based on X-ray magnetic dichroism. What it means is the absorption, scattering, whatever, depends on the relative orientation between the polarization of the light and the magnetization. So You have right circular polarized light, magnetization pointing this way, and you look into the variations when you just switch the polarization. You should get some dichroism. You should also get the same when you flip the magnetic field, and also like this. And all of them should be the same. I'm not sure anymore when we have orbital angular momentum beam that these kind of symmetries will be the same. I would be very, let's put it this way, I'm very optimistic that we'll see some changes in these what's supposed to be a symmetry. And this could be an indication that there's something new happening. It could, for instance, be that the right, left, whatever circular light with the field, because there's more orbital momentum in the beam, all of a sudden changes the spectroscopy signature. And I see our chair getting a little nervous. I'm done. A few open questions for the future. Skyrmion qubits. Again, I started with an open box. I leave the open box still here. Scalability might be a challenge. Materials engineering, precision at atomic scales, when we want to really, manipulate our materials, DMI, control of DMI at a local scale in 3D. This is a challenge. We talked about spatial time resolution, and ultimately, skyrmion entanglement for building some skyrmion qubits. I leave it up to you to come to asking the right question and finding an answer. Thank you. End of course.